Today I will talk about embedding edit distance into Hamming distance. Let me go. Oops. Let me go like very quickly on the basic definitions. I think after Toma's talk we are all aware of them, but so let us go quickly. So generally, when we talk about strings, one very natural thing is to compare like how similar two strings are. And this finds many, many applications. I think I shouldn't motivate that. So let's try two measurements. The first measurement is a very simple one, the Hamming distance. So what do we measure by Hamming distance? We compare two strings, character by character, and check in how many positions are they different. So in this example, I hope you can see the example. We have so the strings are similar except in 3 positions. So the Hamming distance here is 3. Okay. So how about these strings? So one string is 0, 1, 0, 1. Second string is 1, 0, 1, 0. Okay? So if we measure their Hamming distance, then they are different in every coordinate. But I think that in every reasonable measurement, we would like to say that these strings are similar. Okay? So the Hamming distance here is n, but we would like to have like a different measure. So let's talk about the edit measure. So we number how many edit operations are needed in order to convert one string into another. And in this measurement, now these strings are very, very similar. We can do 2 edit operations in order to convert x into y. Okay? So the computational task would be, okay, I'm giving 2 strings. Can we compute their Hamming distance? Can we compute their edit distance? So clearly the Hamming distance can be computed in linear time. But the edit distance takes much longer. It can be done only in a quadratic time. And this seems to me to be optimal under reasonable hardness assumption. So a natural question would be, can we bridge the gap between the metrics? And a natural approach to the bridge is to give an embedding. So let me tell you what embedding means. So we would like to have some function that maps strings of size n into string of size n prime, where n prime, we hope that it would be very close to n. Maybe let's focus on the linear embedding, such that for all pairs x and y, their distances are roughly preserved. What do I mean by that? So if we look on the edit distance between the original string and the Hamming distance between the embedded strings, then we have ideally a linear connection, but dependence, but whatever we can get. Okay, so this is what we call embedding. And one crucial thing about embedding is that the embedding is done independently. We map the string x, we map like the mapping see only the string x, only the string y, and somehow miraculously the edit distance translates into the edit distance of the original strings translates into the Hamming distance of the embedded strings. Okay, so this is an embedding. And our main result, so this is a bit odd result, like from 8 years ago, I think. together with Michal and Diptarka, we show that there is an embedding. The embedding takes strings of length n into string of length 3n. So this is like a linear mapping, such that for all string x and y, the Hamming distance between the embedding is connected to the edit of the original string. So the Hamming distance between the embedded strings is bounded by the edit distance of the original string square, and at least the edit distance of the original strings over 2. Okay? So this is the main result. Also, f is very efficient function. You just make one pass on the string, and based on that, it maps the strings. If we give some more details, so our embedding is not is randomized, which means that the embedding gets two strings. One is what we think of the input string, another is what we think of a random string, and we show that if we embed x and y using share randomness, using the same set of random string, then with high probability over the set of random string, we have the distortion guarantee. So in particular, to make it like more precise, there exists an embedding which takes pair of strings. This is the input string. This is the random string, such that for all pairs x and y, so the probability is not over the pairs of x and y. So for all x and y, we have that with high probability over the random string, if we use the same random string to embed both x and y, then we get the distortion guarantee. Okay? And I will try to show you all the details. So the embedding is very, very simple. Let me tell you. So we scan x from left to right. And then what we do, we go in iteration. So in each iteration, we output the current bit. Then we look on the random string. With probability 1/2, we proceed to the next position. With probability 1/2, we stay on the current position. So the embedding is very, very simple. Okay? Let me write it a bit more formally. So what we have a set of random functions. So we have 3n random functions. So each random function is a function from the alphabet sigma to 0, 1. And then we have two things. So I think of it as a pointer to our string. And t is like the number of the iteration. So in the beginning, we are starting on the first position. So I points to the first position. And then in each iteration, so if we don't reach the end of the string, if the pointer I is smaller than n, then what would be the tth character of the embedded string? It would be like xi. Okay? And then what we do, we choose whether to increment I, whether to increment this pointer according to the random function. The random function, when we apply it on the current character xi. Okay? And if we reach the end of the string, then we just concatenate 0. Okay? So let's do like a very small example to illustrate that. So suppose x is a very short string, the string 0, 1, 0, 1. So at the beginning, I is initialized to 1. Then what we do is that in the first character of the embedded string would be 0. Okay? And then we choose whether we want to increment I or not. And the decision on whether to increment I or not is depend on the first random function, which is h1, applied on xi. So xi, in this case, is 0. h1 of 0 is 0. Then that means we do not increment I in this stage. So in the next stage, we are going to concatenate, again, the first bit of x, which is 0. And then again, we choose whether to increment I or not. Here, like h2 of 0 is 1. So now we choose to increment I. And so on and so forth until we reach the end of the string. Okay? So that's the embedding. Any question about the embedding?
Is
Yes.
R is the same as H, or because you're not using R?
So think of R as representing the random functions. Okay?
There's also the R is same for all strings. So for every R you get an embedding.
So I'm thinking of all pairs of strings, but then for each pairs of strings I can look. So each R gives me a different embedding. So the embedding depends on both the input string and R.
Yes, so the embedding of the entire point set, like the string set that you had, to Hamming space depends on one R, you get one embedding.
So I think what you have in mind is a deterministic embedding, but it is not a deterministic one. So for each pair, like a string and the random string, you get a different embedding. Okay?
So
That's
And if your string finishes, then you just pad it with the last one?
Or just pad it with zeros with some default value. Okay? Okay, so the embedding was very simple, I hope, but why does it work? Why the edit distance of the original string somehow related to the Hamming distance of the embedded strings? Okay? So let us first look on an example. So in this example, we have all ABC. In the first string x, they're just ordered A up to Z. And in the second one, we just take ABC and put it close to the end. Okay? So let's look on this example, like what happens, and then we will do it like more reverse. So at the beginning, so now we will look what happens when we embed x and y using the same set of using the same random string, or using the same set of random functions. Okay? So at the beginning, x, so we have the pointer of x. This points to the first character of x. We have the pointer I of y, which points to the first character of y. And at the beginning, like the first character of x is a, the first character of y is d. So in fx of r, the first character would be a. The first character of the embedding of y will be d. Okay? And we get a mismatch, okay, in the embedded strings. Then what happens? Then what happens next? So now we are going to increment I of x and I of y. But when we increment I of x and I of y, is there any relation between these incrementations? So that's the reason we use this random function, yes? When we apply a random function of a, it has nothing to do with the evaluation of the random function of d. So yeah, I of x and I of y are incremented independently, okay? So then, So then on the next stage, let's say that we choose not to increment I of x, but to increment I of y. And then, again, we have a mismatch. We keep on that like several times. And then, at some point, what happens? At some point, like here we look on I of x, it points to j. And I of y is also points to j. This will happen whenever the difference between I of x and I of y will be 3. If it happens to be this case, then what are we going to output in f of x, in the embedding of x? We are going to output j. But also in the embedding of y, we are going to output j. Okay? So that is a good thing, because now we are not going to see a mismatch. But also another good thing happens. Now when we increment I of x and increment I of y, we will do it on the same way. So that means that from now on, until we see an edit operation, then in the embedding of x and the embedding of y, we will see no mismatches. Okay, so that will go until the next point where we see an edit operation. And then when we see an edit operation, here we point for x, here we point for a. Again, we will have a sequence of mismatching until what happens? Until, again, we will get synchronized. Yes, so at some point, again, I of x and I of y will point to the same character. And if they point to the same character, then there will be no mismatches until the next mismatch. Yes?
So when the alphabet size is strictly greater than 2, you could have it where they're different and yet still do the same thing. But is that not an issue?
So think of alphabet size 2 right now. If it's larger than 2, we can handle that. The same argument works. But if it helps you, you can keep it for okay? So I guess now we have some intuition of why the edit operation between the original strings translates somehow into the Hamming distance between the embedded strings. Okay? So let me try to give it to do it like more carefully. And actually, what we use is a random walk, okay, argument. So let me first define what is random walk. So the rules of the random walk is that there is a drunk man that goes on the integer line. And this drunk man, what he does, he goes in steps, and in each steps, he flips a coin. With probability 1/2, he stays in place. And with probability 1/4, he goes to the right. And 1/4, he goes to the left. Okay? And so I guess many of you have seen that, but if the drunk man starts in the origin, in how many steps will he get to position k? Yeah, so with high probability, if the man makes like c times k squared, where c depends on epsilon, then with high probability, with probability 1 minus epsilon, if he makes more than c k squared, he will reach position k. Okay? So we will use this fact for the analysis. Okay? So let's do the analysis for a special case, but this special case will show all the ingredients of the proof. So suppose we have x and y, which are not of the same length. X has some block B1 of a length k at the beginning, and y is the same string, except that this block B1 is deleted. Okay? So let's make two easy observations. First observation is that in any iteration t, if the difference between the pointer to x and the pointer to y is exactly k, then in all later steps, the value of the embedded string in x and the embedded string of y will be the same. This is exactly what we have when we got a synchronization on the previous example. Okay? So this is one observation. Second observation, if ix minus iy is not k, that means we didn't reach synchronization. And now suppose that we have a mismatch. Like when we look on f of x in the position I of x, and on f of y on the position I of y, they are not equal. Okay? So that corresponds to a mismatch in the embedded strings. So okay, a mismatch in the embedded string is maybe not a good thing, but then a good thing happened. What happened? Then look, if we look on what happens to the difference between I of x and I of y in the next thing, it behaves exactly as a random walk. Since we increment I of x and I of y in such a case independently, then with probability half, it remains the same. And with probability half, it either goes to the left or to the right. So now if we put these observations together, then after c times k squared steps, with high probability that we have a mismatch, with high probability, we will get that the difference between I of x minus I of y will be k, which means that later on, we will not see any further mismatch. So that means that the total number of mismatches will be bounded by c times k squared with high probability. So this is almost a proof for this example, but the proof is not much more difficult in the general case. Okay? So that roughly contains the main idea of the proof. Yes?
Since you're using randomness in this way, you should be able to use expander walks to de-randomize to some extent, right?
So yeah, so we have way to de-randomize and use like much less randomness. Also, I think Michal has a paper that use deterministic random walks.
But not for the embedding. But we can use Nissan's pseudo generation connection.
Yes.
Okay, so let me, yes.
Your probability is like 1 minus epsilon or 1 minus 1 over poly. When you say your probability.
So it is 1 minus epsilon, and then so there is a dependence, like the 1 minus epsilon governs this C term. I think you cannot get with this argument. You cannot get like for the arbitrary probability close to 1, because random walk, when you start a random walk from the origin, it is not true that like with a probability close to like 1 minus little of 1, you will get to k, position k.
It's like, can you do something like many copies of your algorithm or something like that?
Yes, yes. So there are ways to do like many copies of this random walk. So let's have some concluding remarks. So we show an embedding protocol show that there is a quadratic distortion between the Hamming distance of the embedded strings and the edit distance of the original strings. The running time of this embedding is linear, and this protocol is random. now these are thoughts for future directions. So if we think of it like what we show here, we show a way to take to amplify distances. Like we take the distance between x and y, the edit distance between x and y, and this is amplified. This grows quadratically. So one thing is we can think of is, so I show that the Hamming distance between the embedded strings is something between quadratic and linear. So can we specify the cases in which it will be quadratic? That is one thing. Suppose that we can do that. Suppose that you can tell me that on a special family of strings, if we do this, if we apply this embedding, then we always get a quadratic blow-up. Then it seems that this might be like a tool to amplify distances between strings, because you see, you take a pair of strings, then their distance blows quadratically. So then, can we apply it? So can we apply it twice? Can we apply it more? And if we can do that in a meaningful way, then, and also another thing is, instead of considering like the Hamming distance, maybe we can consider the edit distance. So use the same embedding. Can you say that also the edit distance behaves like that? That on a special family of strings, the edit distance blows quadratically. Then that might be a building block to prove some hardness of approximation result for edit distance. So there are many details which are missing in what I said, but this is like a line of thought which might work.
But do you have a lower bound on the expansion? So maybe there is another mapping from n to n log n, and with just linear.
Yeah. In our previous paper, it was like just linear. We saw that the edit distance is at least that the Hamming distance between the embedded string is at least the edit distance divided by 2. And there are examples in which this happens. I can show you some examples in which there is no quadratic blow-up.
No, but this is not what I asked.
So what is the question?
Maybe there is another embedding.
Maybe.
He's asking whether instead of power 2, can you get 1.5?
Yeah.
That's very interesting. If you can come up with not quadratic blow-up, then so I believe that for embedding you cannot do better than quadratic, but if maybe you don't have to restrict.
If you insist on linear,
yes.
or
no, but if you insist of it as being an embedding, as being independent.
But from n to O of n. This is what I mean by linear. So if you allow more, maybe?
I don't think that if you allow more, it will help you.
Okay.
I think you will need quadratic blow-up, but you shouldn't restrict to embedding. Maybe you can do things which are not embedding. You can look on both strings and then maybe get things like not get a quadratic blow-up.
Elazar, won't it violate SETH if you can do linear? Because
yes. Yes, in linear time you cannot get like better than quadratic blow-up. Otherwise, you can use it to get like better than square root of n approximation, and that would violate.
No.
something of
Very
low distortion or something.
Yeah, it's not a lower bound for approximation.
It's not known right now.
Mhm.
He has a
It's
lower
not
bound.
violent strong into it, it's just not known, right? From n plus k squared, you get a square root of an approximation, but there could be other ways of getting square root of an approximation. You don't have to use the exact n plus k squared. You can leave it as
Yes.
an open question. Okay, so let's thank Elazar.